The cold Atlantic waters had become a graveyard. Every 24 hours in 1941, German U-boat were sending roughly 10 Allied merchant ships to the ocean floor. These weren't just numbers on an Admiralty chart. Each vessel carried food, fuel, ammunition, and raw materials that Britain desperately needed to stay in the fight. And the math was brutally simple. If ships went down faster than new ones could be built, Britain would starve long before Hitler needed to invade. By March 1941, Admiral Karl Donitz had perfected his Wolfpack tactics. Instead of solo U-boat attacks, he coordinated groups of 8 to 20 submarines that hunted convoys like predators surrounding prey. They'd surface at night when Allied radar couldn't spot them, torpedo multiple ships in minutes, then disappear beneath the waves before destroyer escorts could respond. The convoys sailed in darkness. Cargo holds packed with wheat from Canada, steel from America, oil from Trinidad, and they died in darkness too, often taking their entire crews with them. The numbers kept getting worse. In April 1941 alone, U-boats sank 168 Allied ships, totaling over 500,000 tons of shipping. In June, another 129 ships disappeared beneath the Atlantic. Britain's merchant marine was hemorrhaging faster than anyone had predicted when war broke out in 1939. Prime Minister Winston Churchill would later write that the only thing that truly frightened him during the entire war was the U-boat peril, not the Luftwaffe bombing London, not Rommel in North Africa, the silent submarinist strangling Britain's supply lines. Here's what made the crisis existential. Britain imported nearly 60 million tons of supplies annually before the war. Food, raw materials, everything an island nation needed to function. By mid-1941, imports had crashed to 30 million tons. Rationing was already severe. Meat portions had shrunk to barely enough for 2 meals per week. Butter, sugar, tea, all controlled by government coupons. Factories were running at reduced capacity because freighters carrying iron ore never made it across the ocean. The Royal Navy had fuel, but just barely. Every tanker that went down meant aircraft couldn't fly, destroyers couldn't hunt U-boat, and the entire war machine ground a little slower. The replacement problem seemed impossible to solve. Britain's historic shipyards in Belfast, Glasgow, and Newcastle were already working flat out. These facilities had been building ships the same way for generations. Teams of skilled riveters hammering metal plates together by hand, one joint at a time. A single cargo vessel took 9 months to a year to complete. The yards couldn't expand fast enough. They couldn't train riveters fast enough. They couldn't acquire steel fast enough. Traditional shipbuilding required traditional timelines, and Britain didn't have months to wait. Admiral Sir Percy Noble, Commander-in-Chief of Western Approaches, Command studied the projections in his Liverpool headquarters. German production was adding new U-boat faster than the Allies could sink them. Donitz had started the war with 57 submarines. By autumn 1941, he had over 200 operational boats with dozens more sliding down German slipways every month. Meanwhile, British yards were completing maybe 4 or 5 new merchant ships monthly. The equation wasn't just unbalanced, it was catastrophic. American shipyards weren't much better. The United States had entered 1941 with a peacetime merchant marine and peacetime production schedules. West Coast facilities were small operations, building a handful of specialized vessels per year. East Coast yards focused on warships for the Navy. Nobody had the capacity to suddenly produce hundreds of merchant ships, and even if they did, conventional wisdom said you simply couldn't rush shipbuilding without compromising quality and safety. Then President Roosevelt made a promise that sounded insane. On January 6, 1941, Roosevelt stood before Congress and announced America would become the arsenal of democracy. The British needed merchant ships immediately, and Roosevelt committed to building 200 standardized cargo vessels as fast as humanly possible. The Maritime Commission nodded and smiled for the cameras. Behind closed doors, they calculated the brutal reality. Traditional shipbuilding methods would deliver those 200 ships sometime around 1945. Maybe if everything went perfectly. Understanding why requires looking at how ships had been built for the past century. Traditional construction was an art form mastered by skilled craftsmen over years of apprenticeship. The process started with laying the keel, then building up the frame with massive steel ribs. Once the skeleton stood complete, workers attached steel plates to the frame using rivets. Thousands upon thousands of rivets. A typical cargo ship required approximately 4 million individual rivets hammered into place by hand. The riveting process itself was almost medieval in its demands. Teams worked in pairs or threes. The heater, boy heated rivets in a portable forge until they glowed cherry red. He'd toss the scalding rivetto the catcher who'd snag it from the air with special tongs and jam it through aligned holes in the steel plates. Then the bucker pressed against the rivet's rounded head with a heavy iron bar, while the riveter on the opposite side hammered the protruding shank with a pneumatic gun, mushrooming it flat. The noise was deafening, the heat unbearable, the pace exhausting. A good riveting crew could place maybe 300 rivets per shift. Do the math. 4 million rivets divided by 300 per day meant over 13,000 working days for the riveting alone. Even with multiple crews working simultaneously on different sections, the riveting phase consumed months, and that's assuming you had enough skilled riveters, which America absolutely did not. Learning to rivet properly took years. The heater had to judge temperature by color. The catcher needed reflexes and precision. The bucker required strength and endurance. The riveter needed to control that pneumatic hammer with surgical accuracy, or risk creating weak joints that would fail at sea. Beyond riveting, every other aspect of traditional shipbuilding demanded specialized expertise. Shipwrights planned the construction sequence, ensuring weight distribution and structural integrity. Marine engineers installed steam engines and boiler systems. Pipe fitters routed miles of plumbing for ballast, fuel, and fire suppression. Electricians wired lighting and communication systems. Each trade had its own apprenticeship path, its own union, its own closely guarded knowledge. You couldn't just grab random workers off the street and tell them to build ships. The maritime unions would riot and the ships would sink. The Maritime Commission surveyed America's existing shipyards. Todd Shipyards in New York, Bethlehem Steels, facility in Baltimore, Newport News in Virginia, Excellent operations all running near capacity, all committed to building warships for the Navy. These yards could maybe possibly squeeze out an extra merchant vessel here and there, if you threw money at the problem. But 200 ships on an accelerated schedule. The Maritime Commission's chief engineer calculated it would require building at least 6 entirely new shipyards from scratch, training thousands of workers in traditional techniques and somehow acquiring enough steel when every industry in America was competing for the same limited supply. And even if you solved all those problems, the timeline remained fixed. A ship took 6 to 12 months to build because that's how long the process required. You couldn't hammer rivets faster without compromising quality. You couldn't cure paint and sealants faster without chemistry changing. You couldn't rush sea trials without risking disaster. Traditional shipbuilding had perfected itself over generations, specifically because shortcuts killed sailors. The establishment knew this in their bones. When some California construction contractor named Henry Kaiser started making noise about building merchant ships, the maritime community dismissed him as a crank. Henry John Kaiser had never set foot on a ship deck as a builder. His expertise came from dirt, concrete, and steel spanning canyons. He'd made his fortune constructing roads in California and Washington, then cemented his reputation by helping build the Hoover Dam and the Grand Coulee Dam. He understood large-scale industrial projects, tight deadlines, and innovative construction techniques. What he didn't understand, according to every shipbuilder on both coasts, was that ships float in water and require entirely different engineering principles than bridges anchored to bedrock. Kaiser didn't care about their skepticism. He saw the shipbuilding crisis through a contractor's eyes, not a shipwright's. When the Maritime Commission issued its desperate call for new production capacity in 1940, Kaiser submitted a proposal that made traditional shipbuilders laugh out loud. He'd build an entirely new shipyard in Richmond, California, hire workers with zero maritime experience, and deliver finished cargo vessels in 60 to 90 days using mass production techniques borrowed from the automotive industry. The old guard called it fantasy. The Maritime Commission, drowning in impossible demands, decided to give the crazy contractor a chance. Kaiser's background actually made him perfect for this moment. During the Hoover Dam project, He'd coordinated 6 different construction companies, orchestrated deliveries of millions of tons of concrete, and finished the job 2 years ahead of schedule. He'd done it by treating construction like manufacturing. Prefabricate components off-site, standardize designs to eliminate custom work, train specialized crews to repeat specific tasks efficiently, work around the clock in multiple shifts. These weren't shipbuilding principles because they'd never been applied to shipbuilding. Kaiser intended to change that. The British had already designed the perfect vessel for his experiment. In December 1940, the British merchant fleet was so desperate they'd ordered 60 cargo ships from American yards based on a steamer design from 1939. The ship was deliberately simple, 441 long, a basic reciprocating steam engine, 5 cargo holds and top speed of 11 knots. Nothing fancy, nothing experimental, just a floating box that could carry 10,000 tons of cargo across the Atlantic. The British called them Empire ships. The Americans would call them Liberty ships after Roosevelt declared 1941 the year of liberty for oppressed nations. Kaiser studied the Liberty ship blueprints and saw something naval architects had missed. The design wasn't a ship. It was a giant 3-dimensional jigsaw puzzle that could be assembled from prefabricated sections. Instead of building the vessel from keel up in one continuous process, why not construct major components separately in dedicated workshops, then crane them into position and join them together? An automotive assembly line built cars from sub-assemblies. Why couldn't a shipyard build ships the same way? The traditional approach built ships from the bottom up because riveting required access from both sides of the steel plates. You couldn't prefabricate a complete bow section in a workshop, because once it was fully riveted together, you couldn't reach interior joints that still needed connecting during final assembly. But Kaiser's team had been watching a different construction method gaining traction in industrial applications. Welding. Instead of hammering rivets, you could fuse steel plates together using an electric arc that melted the metal edges and joined them permanently. Welded joints didn't need access from both sides. A skilled welder could work from one direction and create a seal as strong as a riveted connection. Welding changed everything. If you could weld instead of rivet, you could prefabricate entire sections complete with interior framing. Then weld those sections together. During final assembly, a team could build the bow in one workshop, the stern in another, complete deck sections in a third area, all simultaneously. Instead of 9 months of sequential construction, you'd have weeks of parallel production followed by rapid assembly. The ship wouldn't take less time to build. It would take less time because you'd be building multiple ships at once in component form, then assembling them in sequence. The Maritime Commission awarded Kaiser a contract to build 30 Liberty ships with an option for more if he delivered. Traditional shipbuilders placed bets on when the amateur would fail spectacularly. Kaiser's first Richmond shipyard broke ground in January 1941 on a muddy waterfront lot that had been farmland 6 months earlier. While construction crews poured concrete foundations for workshops and assemblyways, Kaiser's engineers tackled the welding challenge. Electric arc welding existed, but maritime tradition insisted it wasn't suitable for ocean-going vessels. The Navy prohibited welding on warship hulls. Lloyd's of London, the insurance authority for merchant shipping, expressed serious reservations. Every maritime engineer knew riveted joints had proven themselves for 80 years. Welding was experimental, unproven, potentially catastrophic. The engineer sinured tradition and examined physics. A riveted joint worked through mechanical compression. The rivet shank filled a hole drilled through overlapping steel plates, and hammering the ends created clamping force that held everything together through friction. Strong enough for most conditions, but riveted joints had inherent weaknesses. Each rivet hole removed metal, creating thousands of potential stress concentration points. The plates could still shift slightly under load. Riveted holes leaked until the steel swelled from seawater exposure, and even then they continued seeping at the seams. Welding created a fundamentally different connection. The electric arc heated steel to roughly 3,600 degrees, melting the plate edges along with a filler rod. When the molten metal cooled, you didn't have 2 plates held together by a fastener. You had one continuous piece of steel. The joint was as strong as the surrounding plate because metallurgically it was the same material. No holes weakening the structure, no gaps allowing water infiltration, no mechanical parts to corrode or work loose. A properly executed weld was simply better engineering. The training problem seemed insurmountable until Kaiser reframed it. You couldn't train a riveter in less than 2 years because the job required 4 coordinated specialists working in brutal conditions. But welding, one person with an electrode holder and a clear view of the joint could lay a perfect bead after 6 weeks of practice. The skill ceiling was high, certainly, but the skill floor was remarkably low. Anyone with steady hands and good eyesight could learn basic welding. Kaiser's training program didn't need to produce master craftsmen. It needed to produce competent operators who could follow procedures and maintain consistent quality. Richmond Shipyard No. 1 opened its welding school in April 1941. The first classes enrolled shipyard workers transitioning from traditional trades. But Kaiser quickly expanded recruitment. Newspaper advertisements across California announced that no experience was necessary. The shipyard would teach you a valuable trade, pay you while learning, then employ you at wages comparable to skilled craftsmen. Farmers facing drought drove to Richmond. Workers from depression shuttered factories applied by the hundreds. Women showed up despite maritime commission officials insisting welding was too dangerous and physically demanding for female workers. Kaiser hired them anyway. The training program compressed years of apprenticeship into concentrated instruction. Week 1 covered safety, equipment operation, and basic metallurgy. Students learned to strike an arc, maintain proper electrode angle, and control travel speed. Week 2 introduced different joint types and positions. Flat welding on a horizontal surface was easiest. Vertical welding required fighting gravity. Overhead welding rained molten metal on your shoulders. By week 4, trainees practiced on actual ship sections, laying beads that inspectors examined with dye-penetrant tests and X-rays. Students who consistently produced acceptable welds graduated to the shipyard floor. Those who struggled repeated sections until they succeeded or washed out. The difference in labor requirements was staggering. A riveted Liberty ship required 120 riveters working 10 months. A welded Liberty ship required roughly 60 welders working 6 weeks on final assembly, plus additional welders working simultaneously on prefabricated sections. Kaiser replaced 4 million rivets with approximately 30 menace welded seams. Instead of hammering fasteners one at a time, welders fused continuous joints at speeds approaching 12 per minute. The math finally worked. By August 1941, Richmond Shipyard No. 1 had transformed from muddy wasteland into an industrial complex covering over 60 acres. But it looked nothing like traditional shipyards with their massive building slips and towering cranes clustered around a single vessel. Kaiser had designed something entirely different, a factory floor for ship manufacturing. 7 massive assembly ways ran parallel to the waterfront, where finished ships would launch. Behind them stretched dozens of prefabrication workshops organized by component type. Building 1 fabricated bow sections. Building 2 handled sterns. Building 3 produced deck panels. Building 4 assembled deckhouse structures. Each workshop operated like a dedicated production line feeding the final assembly ways. The prefabrication system worked like this. Engineers divided the Liberty ship design into roughly 250 major sub-assemblies. Each sub-assembly was small enough to be built in a workshop and transported by crane, but large enough to minimize final assembly time. A complete bow section might weigh 30 tons and include the outer hull plates, interior framing, bulkheads, and piping already installed. Workers built these sections on specially designed jigs that held all the components in precise alignment, while welders joined them. The jigs were reusable patterns identical for every ship, eliminating the custom fitting that consumed weeks in traditional construction. The workforce assembling these sections looked nothing like a traditional shipyard crew. By October 1941, Richmond employed over 15,000 workers. 60% had never worked in heavy industry before. The yard hired Edgar Kaiser, Henry's son, specifically tonnage personnel and training. Edgar walked the yard floor and saw former school teachers learning to operate overhead cranes. Dust Bowl refugees from Oklahoma operated cutting torches. Housewives from Oakland welded bulkheads. Retirees who'd spent careers farming installed piping systems. The oldest welder was 67. The youngest was 19. Women comprised roughly 30% of the workforce by 1942, shattering every assumption about industrial capability. Wendy the welder became a recruiting poster icon. But thousands of real women performed every job in the yard except the heaviest lifting. They welded as accurately as men. They operated cranes with precision. They read blueprints, performed inspections, and supervised construction crews. The yard paid equal wages for equal work because production quotas mattered more than gender politics. If you could do the job, you got the job and the paycheck. The yard operated 24 hours daily in 3 8-hour shifts. First shift started at 7 in the morning. Second shift began at 3 o'clock in the afternoon. Graveyard shift ran from 11 at night until 7. Workers arriving for each shift found their assigned stations already set up with materials and equipment. Prefabrication workshops maintained continuous production, feeding completed sections to the assembly ways where they'd be installed during that shift's allocation. The night crew picked up exactly where the day crew stopped, following progress charts updated hourly. Kaiser organized work teams around specific repetitive tasks, rather than traditional trades. One team did nothing but weld longitudinal seams on hull sections. Another team specialized in connecting bulkheads to frames. A third team exclusively installed piping bundles. This specialization meant workers achieved expertise quickly, in their narrow domain rather than spending years learning an entire trade. A welder who spent 8 hours daily welding the same joint configuration in the same position became extraordinarily efficient at that specific operation. Traditional shipwrights called it desk killing. Kaiser called it productivity. The assemblyways operated on a schedule synchronized across all 7 positions. When Ship 1 finished and launched, Ship 2 moved forward 1 position. Ship 3 advanced to position 2 and so on. A new keel was laid in position 7 the same day. Like automobiles moving down an assembly line, ships progressed through stations where specific work happened at each position. Early stations installed the bottom hull sections and engine room components. Middle stations added deck structures and superstructure. Final stations completed outfitting with equipment, piping, wiring, and paint. Every ship spent approximately the same time at each station, creating predictable workflow and resource allocation. The first Liberty ship completed at Richmond, the SS Patrick Henry, launched on September 27, 1941 after roughly 150 days of construction. Traditional shipbuilders nodded knowingly. See, they said, Kaiser's revolutionary methods delivered a ship in 5 months instead of 9. Impressive for an amateur, but hardly the miracle he'd promised. They stopped talking 3 months later when Richmond launched its next ship after 90 days of construction, then another after 75 days. By spring 1942, Richmond was completing ships every 40 days, then every 30 days, then faster. What the skeptics failed to understand was that Kaiser's system needed time to optimize. Those early ships taught the workforce how prefabrication worked, revealed bottlenecks in the process, and proved which innovations succeeded. By the time Richmond Shipyard No. 2 opened in January 1942, Kaiser's team had refined their methods into a genuinely revolutionary system. The second yard incorporated lessons from the first with better workshop layouts, improved jig designs, and streamlined material flow. Production times collapsed. Competition between Kaiser's yards intensified throughout 1942. Richmond Shipyard No. 1 completed a Liberty ship in 41 days. Richmond No. 2 countered with 37 days. No. 1 responded with 33 days. Workers checked production boards obsessively, tracking which yard held the record. Management encouraged the rivalry, offering bonuses to teams that beat previous records. The competition wasn't just internal. Kaiser's operations competed with Oregon Shipbuilding in Portland, another Kaiser-managed facility, and with other shipbuilders up and down the West Coast. The records fell with dizzying speed through autumn 1942. Oregon Shipbuilding completed a Liberty ship in 30 days. Richmond No. 2 answered with 27 days. In early November, Kaiser announced that Richmond No. 2 would attempt something unprecedented, building a complete Liberty ship in under 1 week to demonstrate American industrial might for a visiting delegation of Allied officials and to raise money for war bonds. The Maritime Commission thought he'd lost his mind. A week to build a ship impossible. Kaiser chose the SS Robert E. Peary for the record attempt, named after the Arctic explorer. Richmond No. 2 had been preparing for weeks, stockpiling prefabricated sections, training crews in rapid assembly procedures, and choreographing every movement like a military operation. The keel touched down on the assemblyway at 12:01 a.m. on Sunday, November 8, 1942. Over 4,000 workers swarmed the site across all 3 shifts, working with surgical precision. Massive cranes lowered prefabricated hull sections into position every few hours. Welding teams warmed each joint, working simultaneously on dozens of connections. The bottom hull took shape in 16 hours. Engine room sections dropped into place on Monday morning. By Monday night, the deck was going on. Tuesday brought the superstructure, deck houses, and masts. Wednesday focused on outfitting, miles of piping, electrical systems, ventilation equipment, cargo booms, lifeboats, and navigational equipment. Thursday morning, painters applied the final coat while engineers conducted system tests. Thursday, November 12th at 3:30 p.m., exactly 4 days, 15 hours, and 29 minutes after the keel was laid, the SS Robert E. Perry slid down the ways into San Francisco Bay, fully operational. The ship had functioning engines, loaded fuel tanks, working steering, complete electrical systems, and passed every safety inspection. Photographers captured the moment. Newser cameras rolled. The crowd of workers and officials erupted in cheers. Kaiser had built a 10,000-ton cargo ship in less time than it took traditional yards to finish the riveting. The record was technically a stunt requiring extraordinary preparation and resources, concentrated on one vessel, but it proved Kaiser's methods worked. By the end of 1942, America's new shipyards were averaging 42 hours between Liberty ship launches across all facilities, not 42 hours to build one ship, but a new ship sliding into the water every 42 hours because multiple ships were always under construction, simultaneously, at various stages. The production numbers tell one story. By the end of 1943, American shipyards delivered over 1,200 Liberty ships. Kaiser's yards alone produced over 750 vessels. The United States was launching 3 ships daily, overwhelming German submarine production by a factor of 10 to 1. Admiral Donitz watched his wolf packs sink fewer ships each month, while Allied convoys grew larger and more numerous. By mid-1943, convoys crossing the Atlantic delivered 11 million tons of cargo monthly, more than replacing losses. The U-boat menace hadn't disappeared, but the stranglehold had broken. Britain received food, fuel, ammunition, and equipment in quantities that made invasion planning possible. Liberty ships were winning the Battle of the Atlantic. Then ships started breaking in half. The first catastrophic failure happened in January 1943. The SS Schenectady, barely 3 months old, sat docked in Portland Harbor in calm water when crew members heard a sound like a rifle shot. A crack appeared in the deck, raced along the hull, and split the ship completely into just after the bridge. The stern section sank. The bow settled onto the harbor bottom. The ship hadn't hit anything. No explosion, no storm damage. It simply fractured while sitting peacefully at the dock. Engineers initially dismissed it as a freak accident, possibly bad steel or improper welding. Then the SS John P. Gaines broke in half near Seattle. The SSSO Manhattan cracked while sailing in moderate seas. By March 1943, over 20 Liberty ships had experienced serious structural failures. Some developed cracks that could be repaired. Others broke catastrophically. The Maritime Commission couldn't ignore it anymore. Something was fundamentally wrong with welded ship construction. The investigation revealed a phenomenon called brittle fracture that naval architects had never encountered at this scale. Steel normally behaves in a ductile manner, meaning it deforms and bends before breaking. You can see this with a paperclip. Bend it back and forth and it gradually hardens before finally snapping. But under certain conditions, steel transforms from ductile to brittle, shattering like glass with almost no warning. The conditions that trigger this transformation are low temperatures, high stress concentrations, and specific metallurgical factors. Liberty ships sailed in North Atlantic waters where temperatures dropped below freezing. These steel plates used in construction came from mills producing to minimum specifications for cost efficiency. Some batches had high sulfur content which reduced ductility. The ships operated with heavy cargo loads that created constant stress on the hull. But the critical factor was welding itself. A welded seam created a continuous stress path across the entire structure. In a riveted ship, cracks forming at one rivet couldn't easily propagate because the next rivet hole interrupted the stress field. In a welded ship, once a crack started, nothing stopped it from racing along the entire weld seam. The problem intensified at corners and cutouts. Every hatch opening, doorway, and window created a stress concentration point where forces focused. Traditional ships had rounded corners and gradual transitions that distributed stress. Liberty ships built for speed and simplicity used square hatches with sharp 90-degree corners. Engineers call these stress risers. When brittle steel under tension encountered a stress riser, catastrophic fracture could initiate from a welding flaw smaller than a pinhead. Constance Tipper, a British metallurgist at Cambridge University, led the scientific investigation. Her research demonstrated that the transition from ductile to brittle behavior, occurred at specific temperatures depending on steel composition. Lower quality steel transitioned at higher temperatures. Many Liberty ship plates became brittle at temperatures commonly encountered in winter Atlantic crossings. She also proved that welding altered the steel's grain structure in the heat-affected zone next to the weld, creating regions more susceptible to brittle fracture. The Maritime Commission faced a nightmare scenario. Over 2,000 Liberty ships were either completed or under construction using identical designs and methods. The fix came faster than anyone expected because Kaiser and the Maritime Commission couldn't afford to stop production. Engineers retrofitted existing ships with crack arresters, steel straps riveted across vulnerable areas to stop fracture propagation. Naval architects redesigned hatch corners, replacing sharp angles with rounded transitions that distributed stress smoothly. The Maritime Commission mandated higher quality steel with lower sulfur content and better low-temperature properties. Most importantly, welders received additional training in proper technique, focusing on eliminating the tiny flaws that could initiate cracks. The redesigned Liberty ships designated EC2SC1 in official documentation incorporated these fixes from the keel-up rounded hatch corners, crack arter plates built into the structure, better steel specifications, more rigorous welding inspection using X-ray and ultrasonic testing. The modifications added roughly 3 days to construction time and increased costs by about 8%, but ships stopped breaking. By late 1943, catastrophic fractures essentially ceased while production barely slowed. The lessons learned from failure made welded construction stronger than riveting ever was. By the time Germany surrendered in May 1945, American shipyards had delivered 2,710 Liberty ships. Kaiser's operations built over 400 of them. The total construction time for the entire program, roughly 4 years to build more tonnage than existed in the entire pre-war American merchant marine. The ships carried 7 million tons of cargo to European and Pacific theaters. They transported tanks to North Africa, ammunition to Normandy, and food to liberated populations. 72 Liberty ships were lost to enemy action, weather, or accidents. The rest sailed through the war and continued serving for decades afterward. The revolution Kaiser unleashed didn't end with victory. Traditional shipbuilding died in those California and Oregon yards. After the war, no major shipyard returned to riveting. Welding became the universal standard for ship construction worldwide. The techniques developed under wartime pressure, refined through catastrophic failure and engineering analysis, established the foundation for modern maritime engineering. Today's container ships, oil tankers, and naval vessels all descend directly from Kaiser's welded Liberty ships. The prefabrication methods proved even more revolutionary. Modern shipyards from South Korea to Finland build ships exactly as Kaiser did, construct massive sections in specialized workshops, then assemble them rapidly at the waterfront. The vocabulary changed. They call them modules now instead of sub-assemblies, but the principle remains identical. Contemporary shipbuilders produce vessels in months rather than years. Because Kaiser proved that parallel production beats sequential construction every time, the human impact matched the technical revolution. Over 1 million Americans worked in wartime shipyards, learning industrial trades that supported them through decades of post-war prosperity. Women who welded Liberty ships became machinists, electricians, and factory supervisors. Men who operated cranes built the suburban homes and urban infrastructure of 1950s America. The shipyard training programs demonstrated that ordinary people could master advanced technical skills quickly if given proper instruction and opportunity. That lesson influenced everything from the GI Bill to community college systems. Kaiser himself leveraged wartime success into a business empire. Kaiser Steel, Kaiser Aluminum, Kaiser Permanente Healthcare. His belief that industrial efficiency could solve social problems shaped mid-century American capitalism. Critics noted he'd become wealthy building ships with government contracts and subsidized steel. Supporters pointed out he'd delivered exactly what the nation needed when traditional experts said it couldn't be done. The Liberty ships themselves sailed for decades after the war. Some carried cargo commercially until the 1970s. 2 remain operational today as museum ships. The SS Jeremiah O'Brien, permanently moored in San Francisco, still has its original reciprocating steam engine and can sail under its own power. Stand on that deck and you're standing inside the ship that proved welders could outbuild the world.